Hello, welcome. Hope you're alright. This is a short presentation about OpenGL. OpenGL is basically a cross-platform library for 3D graphics. It's less verbose than Vulkan, but even if you want to later move on to Vulkan, the knowledge, OpenGL knowledge is transferable to Vulkan. And OpenGL also has bindings for many programming languages. Here's a few examples what has been accomplished with OpenGL. There's, for example, Minecraft Java Edition, which is using OpenGL. There's Stellarium. Then also WebGL is basically based on OpenGL. And for example, Google Earth is implemented with it. And last but not least, there's a KDE Plasma Desktop, which also uses OpenGL. In order to get started, we'll use GLEW and GLFW. GLEW is basically a library which provides a C header to access the OpenGL functions from the graphics card. And GLFW is a cross-platform library for opening windows and handling input and stuff like that. So here's a minimal program. Basically, it uses GLEW and GLFW. It opens, initializes the window. It makes a context current. And then here are two functions. One for setting the clear color, and in the loop performing the clear operation, and then swapping the buffers and doing that until the window should close. And when you compile that program, that's the result you get. You basically get a window with dark gray content. The next step is a bit more involved. So in order to get something, some objects on the screen, we need to implement the vertex shader and a fragment shader. So OpenGL basically in this minimal pipeline setting, it'll fetch vertex data, pass it through the vertex shader, and then a rasterizer will render the triangles. And for each pixel, invoke the fragment shader, and that output then is used for frame buffer operations. So here's a very simple vertex and fragment shader. The vertex shader just takes a point from the vertex data and outputs it to GL position, which is a system variable, basically a standard output from the vertex shader. And the fragment shader in this simple example just outputs a red color. We can put these two shaders into C strings, and then we can use a few OpenGL calls to create shaders, set the source code for each shader, and compile the two shaders and handle errors. And at the end, at the bottom, you can see we create a program. We attach the shaders, and then we link the program and handle errors again. Error handling is very useful for finding out if there's something wrong with your shaders, so it's really important to implement this. So you basically check the compile status of the shader. If the result is false, you can use GL get shader info log to get the error message. And linking looks very similar. You check the link status, and again you get the error information if the link status is false. We need some data to as an input for the OpenGL pipeline. So we just need points at the moment. So points are x, y, z. So here we have a vertices array which contains 4 points. And we have a index array which indexes the vertices in counterclockwise order. And we allocate 3 variables, one for vertex array objects, vertex buffer objects and for the index buffer. On the right side you see the normalized device coordinates. It's a normalized coordinate system which OpenGL uses, where every value, every axis x, y, and z goes from -1 to +1. So in order to pass the vertex and index data to the pipeline, we need to put it into buffers. So you have the array buffer and the element array buffer, and at the top we have the vertex array object. Vertex array object is like a context for switching between different array buffers. We also need to tell OpenGL, we need to tell the pipeline how the data is organized. In this simple case, we just have a point variable, which is 3 floating point numbers, and one row is 3 floating point numbers as well. And the offset for the point in each row is 0. Then we use GLU's program to set the current program, and we enable the first vertex attribute, which is basically the point. And then we just call GLDraw elements in the loop, and that will perform the rendering operation. And at the end we need to clean up the array buffers and the shaders. And after all this, finally you get a red rectangle. To make things more interesting, we can use textures. In order to use textures, in order to perform texture mapping, we need to have texture coordinates. So we assign texture coordinates to each point. So now the vertex array has 5 elements in each row, x, y, z, and the u and v are the texture coordinates. And here we define a very simple texture with 4 pixels. The checker variable contains 1 gray pixel, 1 white pixel, another white pixel, and then a gray pixel again. So we're going to use it as a 2x2 checker texture. We need to extend our pipeline, our shaders. So in the vertex shader at the top, we add the input, the 2-dimensional texture coordinate as an input, and we add the 2-dimensional texture coordinate UV as the output, and we just pass it through. So we say UV equals tech coord. And later in the fragment shader, we use the texture and the UV, which gets interpolated by the rasterizer. And then we use the texture method at the bottom to do a texture lookup. We take the RGB value and assign it to the fragment color. And again, we need to set up the variables, the memory layout. So now we have 2 variables, point and tech coord. Point is 3 floats, tech coord is 2 floats. One row is now 5 floats, and the offset for tech coord is 3 floats. So it's after the point in each row. And we need to enable both vertex attributes, 0 and 1. And we need to also load the texture into OpenGL. So we activate the texture slot 0. We bind the generated texture variable to texture 2D. And then we also point the tech variable of the program to the texture slot 0. And then we use GL tech image 2D to load the texture, the 2x2 texture into OpenGL. And then there are further parameters we can set. So we set the texture wrapping to repeat. So when the texture index exceeds 1, we just repeat the texture. We do that in both dimensions. And regardless of the texture size, whether it's magnified or not, we set the interpolation to nearest. And at the end we need to tidy up. So we unbind the texture and we delete it. And when we run that program, we now have a checkerboard basically with lots of squares. So this was all two-dimensional. In order to do three-dimensional rendering, we can use rotation matrices to change the orientation of the rectangle. So here we have two uniform rotation matrices. Uniform means they stay the same for all shader invocations. And then we set pos to rotation x times rotation z times point, and we output that point. That's actually wrong, that should be pos. GL position should equals vec4 pos comma 1. And then we pass through the texture coordinate as usual. We set up the matrices as follows. So we create a rotation matrix and we use GL uniform matrix 3FV to load the matrix into OpenGL. We do that for the rotation Z and the rotation X matrix. And then we get the following result. It's still it's 3D, but it's still isometric. So in the following, we're going to use projection matrices, but first we are going to enable depth testing. So we set the depth function to greater or equal, and we set the clipping to lower left coordinate system origin, and we set the clipping to 0 to 1, and the clear depth, the initial depth is 0. Then we enable depth testing, and in the loop we now also clear the depth buffer in addition to the color buffer. So this is a projection, the frustum. That's basically the viewing pyramid. You can find the details on how this projection matrix is derived on my webpage. The link is at the bottom. Basically, we scale x and y depending on the field of view. So the smaller the field of view, the larger dx is, the more we need to scale up x. And y is similar to dx, but it's modified to have the correct aspect ratio. So because the screen is not as high as wide, the height of the screen is less than the width, we need to scale dy, the y coordinates more than the x coordinates because the field of view in y direction is smaller. And then we use a and b to map the z range of minus near to minus far to be between 0 and 1. And the denominator for the projection, we need to divide the coordinates for projecting by minus z, so that's why we have a minus 1 in the matrix. So as you can see, on the left side, the coordinate system is such that the z vector is pointing out of the screen, so everything you can see in the scene is going to have negative z coordinates. That's just a convention which is commonly used. So now we extend our vertex shader to use a uniform projection matrix and a uniform distance as well. So I first do a translation. vec3 translation equals vec3 0 0 comma minus distance. And we, again as before, we perform the rotation around x and z axis of the point. And we add the translation vector. And the result is going to be extended to a four-dimensional vector by adding a 1. And then we multiply that with the projection matrix and that's assigned to GL position, the projected coordinates. And as usual, we pass through the texture coordinates. The math from the 2 slides ago is implemented like this. And the matrix using GL uniform matrix for FV is used to pass the matrix to OpenGL again. And then the result looks like this. So now this is proper projective graphics. The next thing we're going to look at is a full OpenGL pipeline. So the full OpenGL pipeline consists of a vertex shader again, but now it's followed by a tessellation control shader, which controls how many vertices are created, and a tessellation evaluation shader, which then uses tessellation coordinates to generate vertices, and we use a geometry shader to modify those vertices. And finally, we have the fragment shader as usual. So this is an example where a quad is tessellated into many small triangles. So you have an inner quad count, inner count of squares, and you also have outer counts. So you can have different outer counts. So at the bottom, for example, we only have 2 points. On the right side we have 3 points. At the top we have 4 points, and on the left side we have 5 points. So you can basically set the inner and outer tessellation level in order to do tiling with other quads with different amounts of tessellation. So you can create very complicated meshes with adaptive resolution. So our vertex shader, I just renamed UV to UV underscore vert to distinguish it from other variables, and I assign it the texture coordinate as before. And the tessellation control shader, it takes as input 4 vertices. It takes as input 4 UV coordinates, and outputs 4 UV coordinates. And this tessellation shader is gonna get invoked 4 times for our quad, and with GL invocation ID set to 0, 1, 2, or 3. And we set in the first invocation, we set the tessellation level. Here we set everything to 25. And we set the system variable GL position to the input GL position. And we set the output UV control shader, the UV underscore contour. We set it to the UV from the vertex shader, the UV underscore vert. And now this is the tessellation evaluation shader, or part of it, the first part of it. So we perform the rotation and projection in this shader because it's different for each point. And we output the UV coordinates as well. And we're going to use a function to modify our Z coordinates. So I'm going to use a radial sinc function, a sinus x divided by x function, with an amplitude of 0.4 and a scale of 30. So we define sinc of float x. So you can see you can define functions in your shaders. You can even put them into separate strings or files and link them later. And here we have a sinc function, which is basically sinus x divided by x, or 1 when x is 0. And the function f is defined on 2D vectors. It's basically the sinc of scale times the length of the vector times amplitude. And the rest of the tessellation evaluation shader is like this. So we use the mix function to interpolate between the 4 quad corners, and we get gltestcore.x and gltestcore.y as input, and we use testcore.x to interpolate between point 0 and 1 as well as points 3 and 2, and the two results we then use for interpolating according to gltestcore.y, and we override the z coordinate with the function applied to pos.xy, and then we take this position, and as before we translate it, we create a translation vector, and then we take this position, rotate it around z, rotate it around x, add the translation vector, extend the vector with a 1 to get a 3D homogeneous vector, multiply that with the projection matrix to get the projected coordinates. And furthermore, we take the UV coordinates, and we, same way as we did for position, we are going to interpolate between the different UV coordinates to generate the output UV coordinates. And then finally we have the geometry shader. This geometry shader does nothing but just pass through the triangles it gets. So it'll read out the position 0, GL position of input 0, write it to GL position, set UV to the UV eval input in the emitter vertex. It'll do that 3 times for the 3 points, and then it emits it ends the primitive, it ends the triangle. So this is a trivial vertex shader, but you can, geometry shader, but you can of course use geometry shader to do other things, like for example doing an exploding view or something like that, or displaying normal vectors. And finally we have the fragment shader, which is as before, we just do a texture lookup using the texture coordinate UV. And as we did for the vertex and fragment shader, we also need to compile the tessellation control shader, the tessellation evaluation shader, and the geometry shader. And we add them to the attach instructions. So we add attach instructions to attach all 5 shaders, and then link the program. And important, we don't use GL quads as a draw elements argument. We use GL patches this time. And we also need to set the GL patch vertices to 4 before calling GL draw elements. And finally, we need to tidy up the cleanup, delete the shaders. And then the result looks like this. The result looks a bit flat. So the next thing we're going to look at is diffuse lighting. So what I've done here, I've put the function into a maxima, a symbolic math program, and computed the derivative. And this is basically for vector, two-dimensional vector v, it'll output a two-dimensional derivative. So derivative in x and y direction. And what we now do is we add an additional output to the evaluation shader, which is a normal vector. The normal vector is just is composed from minus the gradient and 1 as z coordinate. And you also need to rotate this normal vector using the rotation matrices. And in the geometry shader, we just pass through this normal vector. And in the fragment shader, we take in a uniform light vector, which is the direction to the light source. We take the normal vector input, and then we take the dot product, we normalize the normal vector because it's not going to be length 1 normally. And then we can take the dot product of the light vector and the normalized vector, normal vector, and we take the maximum of that and 0 to make sure we don't get negative values in our brightness. And this is basically the cosines of the incident angle of the light for each surface pixel. This tells us how bright this pixel should be. We also add an ambient term so that dark regions are not going to be black. We basically add ambient and diffuse component and multiply that with the color. And when you, then you need to, in the program, you need to set up the light vector. So here we just say x, the direction is xy, identical component. So it's 45° upwards to the right is the light source. And then we use GL uniform 3FV to set the light vector. And then it'll look like this. So this was a short presentation. There are further topics which are interesting. For example, face culling is very good for optimizing, for improving the performance. We only did diffuse lighting. There's also specular lighting, which you can read about when you look for Phong shading. Normal maps are very interesting to generate rough surfaces. Fog is easy to do. Then there's shadow mapping, volumetric rendering, for example, volumetric clouds. And more modern than Phong shading is physically based rendering, is an umbrella term for some improved rendering techniques for generating photorealistic images. Then GLTF asset import is quite useful to generate. So you can use a Blender, for example, to create complex surfaces and then import them using GLTF. There's also so-called ASDO features, approaching zero driver overhead features in OpenGL. So you can do instanced renderings and things like that, so that the CPU overhead for instructing the graphics card is as low as possible. And there are also compute shaders for doing computations instead of graphics on the GPU. So I can really recommend to read this book, the OpenGL Super Bible. You can get it from informate.com as a DRM-free PDF file or EPUB. And also there's learnopengl.com. The author of learnopengl.com even provides a free PDF book. And you can also buy a print edition. And another interesting website to check out is shadertoy.com, which is a community website where people share their shaders and results. So you can run the shaders straight in the browser and look at the results. And yeah, that's basically it. So let me know any comments or questions or suggestions in the comment section below. And yeah, thanks for listening and have fun with OpenGL.